Hi again, welcome to another review session for your final exam in Calculus 3208, brought to you as always by CBLI, and today we're looking at indefinite integrals of polynomials and indefinite integrals of polynomial-like functions. So we're going to introduce the concept of the indefinite integral and what it means and how it's related to what we already know about the antiderivative. So we're going to look first of all about at integral notation. And from there, we're going to look at rules for integrals, or for indefinite integrals. And then we're going to talk about integrating polynomials and polynomial-like functions. Okay, so let's get down to business. Antidifferentiation. Well, we should know about that by now. We know that if I have a function f of x that's equal to 10x, then capital F of x equals 5x squared plus c. That would be its antiderivative. So the antiderivative of this is that. Now, the problem with just talking about antiderivatives in that way is that it's okay to have two different notations and everything seems to work, but it's kind of cumbersome. Like, there's no operator I can say, so take the antiderivative of this and give me an answer. It's not as sleek as we'd like it to be. But when we use indefinite integral notation, what that does is it adds that element of sleekness to it. So what I want you to do is look down here where it says indefinite integration. So we look at this notation right here. And the first thing you'll notice about that notation is that there's this big funny character right here in the front. And that is the integration, or the integral symbol. And basically it just looks like a capital or a really tall stretched out S. That's kind of what it is. So people draw them in all kinds of different ways, but that's basically right here is the standard of what you're going to see for an integral. And no integral is able to stand on its own. It always has to have a partner or a buddy with it. And every integral has a friend that comes at the end of the integral statement, and it's right here, and it's this little differential, we call it dx. And that's the same dx that you would see if you had a derivative that says dy over dx. So it's just this part of that, okay? So you can almost think of integral notation as being like brackets or some sort of flanking device, if you will, where we've got this thing at the beginning and the dx at the end. And the stuff that we're trying to find the indefinite integral of, which basically is just the antiderivative of, is everything that's written inside there. So these two things on the end here tell us I just want to find the antiderivative of y equals 10x. And so that's 5x squared plus c. And that's all there is to it. So that's all that funny notation means. You can't have one without the other. You have to have both things, and there's on the outermost extremes, and everything inside there is what you're finding the integral, or the antiderivative of. Okay. So when I read that from left to right, I say, okay, I'm going to have an indefinite integral of 10x dx, or you can just say 10x, and it's equal to 5x squared plus c. Okay? So that's how we read that. So let's take a look now. What I've done here is I've recreated a table of rules for integration. And these are essentially the same rules that we had for antidifferentiation, except we're going to write them now using the proper integral notation. So the integral of x to the power of n dx, we already know is going to be x to the power of n plus 1 over n plus 1 plus a constant c. But be forewarned, we know that n is not allowed to equal -1, or we can't integrate in that way. All right? So the integral of the sum or difference of two functions is just the sum or difference of the two integrals. Okay, so that's another rule we knew. And if I have the integral of a constant multiple of a function, I can pop that constant right outside, so take it right out in front of the integral here, and I have a, or the constant, times the integral of f of x dx. And on the end there, I've got the integral of k times dx. And of course, if k is a constant number, like 5 or 12 or -3 million, then the antiderivative, or the indefinite integral, is just going to be kx plus c. Okay? So those are rules that we knew, but just sort of presenting them in the light of our new notation that we have for dealing with it. All right, let's take a look at some stuff now. Here's an example. Compute the indefinite integral of each polynomial function. So basically, we're finding the antiderivatives of the stuff that's wedged between the integral symbol and the dx. So what are we going to get here? For the first one, 3x squared. So the antiderivative of that will be 3x cubed divided by 3 minus. The antiderivative of 2x will be 2x squared divided by 2. And the antiderivative of of 1 will just be x, and then I always add an arbitrary constant. And then we simplify what we can. So this is a nice one. Look, all these things just kind of cancel out, and we get x cubed minus x squared plus x plus c. Okay, so not much to that at all. So for the next one here, we've got to take the integral of 5x minus 17x to the power 4 plus 3x to the power 7. So let's try that one. So the 5x will become 5x squared divided by 2. And 17x to the power 4 will be negative 17. X to the power 5 on 5. Plus, we're going to have for the last one, 3x to the power of 8 over 8. And then plus our arbitrary constant. And unfortunately, nothing is going to get any prettier there than it already is, so we have to deal with that. So we're going to have to leave fractions floating all over the place there. Okay, so for the next one, now let's see what we have. The antiderivative of 6x to the power 5 plus 3x squared minus 2x plus 12. All right, let's go after this. So we're going to have 6x to the power of 6 divided by 6 plus 3x cubed over 3 minus 2x squared over 2 plus 12x plus our arbitrary constant. And that one is going to simplify. So 6x to the power of 6 over 6, the 6's go away. Here the 3's will be gone, and 2 divided by 2 is also 1, so they can go. So we're just going to have x to the power of 6 plus x cubed minus x squared, 12x, whoops, the 12 got a little bit cagey, 12x and c. Okay, so there's our antiderivative for that one. You can always check antiderivatives to make sure you got them right, or indefinite integrals to make sure you got them right. Go ahead and differentiate and see if you get back to the same place. For example, with this one I just did, I'm going to take the derivative of this and see if I get the same thing. So the derivative would be 6x to the power 5 plus 3x squared minus 2x plus 12. And then the c goes to 0. And that's exactly what we have over here. There's no more it's not a more complicated process to anti-differentiate than just to differentiate. But most of us are probably, especially at this point in the course like this, so used to taking derivatives that to think backwards takes a little longer. All right, let's try another example now. You'll notice at the beginning of this session, and I'm just going to skip back some slides and show you. At the beginning of this session, I said we were going to talk about integrating polynomials and polynomial-like functions. So let's take a look at this example now that we just hauled up here. It says, compute the indefinite integral of each polynomial-like function. These aren't polynomials, but what we can do with each one of them is we can just sort of tweak the expression that we have a little bit to make it look like a polynomial, and then use our power rules for anti-differentiation. Very similar to stuff that we used to do with derivatives before we had any other way to differentiate other than just the power rule. So let's try this. So for this first one, I'm going to rewrite it first of all. I'm going to say that this is just going to be the antiderivative, or the indefinite integral of t to the power of negative 2 times dt. Okay. So then I have to follow the power rule to anti-differentiate. So remember, I increase the exponent by 1, so this becomes t to the power of negative 1 divided by negative 1, and then plus my arbitrary constant. Now I don't like the way that looks because I don't like to leave a negative 1 denominator, and I don't like to have a negative exponent. So to be more concise, this could actually be written as negative 1 over t plus our constant. So that's a much nicer way to present that answer. Okay? Let's try the next one. So for the next one, we've got the integral of the square root of z dz. So let's first of all make it look a little more polynomial-like. So this will be the integral of z to the power of 1/2 times dz. Okay, so now that it looks like a power function, I can integrate it using my rules for power functions. So that's going to be the integral. Oh, once I integrate, I don't need my integration symbol anymore. And now I'm actually integrating, or I'm anti-differentiating. And once I get to that step, then I have to eat that sign. I'm not allowed to keep it around anymore. So this is actually going to be equal to z to the power of, increasing that by 1 is like 2 over 2. So this will be 3 halves, oops, and then divided by 3 over 2. So I'm going to say multiplied by 2/3, which is the same thing. So if I simplify this, oh, forgot my constant, and if I simplify this, I've got 2 times the square root of z cubed all over 3, or you could just put 2/3 out the front, would be the same thing, plus your arbitrary constant c. So there's the antiderivative or indefinite integral of that one. Okay, for this last one now, what are we going to do about this last one? Let me think. We've got to take the antiderivative of x plus 1 over x cubed. Well, we don't know how to integrate a quotient like that yet, so we got to make it look like a polynomial. So I'm going to take the antiderivative of x divided by x cubed. I'm going to say that that's x to the power of -2, and then 1 divided by x cubed will just be plus x to the power of -3. And technically, you can probably get away without them, but technically there should be brackets there now, times dx. So that's going to be equal to anti-differentiate, remember I increase my exponents by 1, and then divide by my new exponent. So this will be x to the power of -1 over -1, plus x to the power of -2 over -2, and then plus my arbitrary constant. So now to write that in a more professional looking form, I suppose, it'll be -1 over x minus 1 over 2x squared, and then plus our constant. Okay, so there's the antiderivative of that one. All right, one more example, I think, before we turn loose on some stuff here. So let's jump along. Now in this case, we've got some even more complicated expressions that we have to try to anti-differentiate. So let's see what we can come up with. So before we do that, it's probably best to write each of them in a little more friendlier form. So we've got the integral for the first one is going to be 6 times t to the power of 1/3, and then subtract t to the power of -2, and then dt. So when I do that, what I'm going to end up with is, increasing my exponent there by 1 would give me 4/3. So this will be 6t to the power of 4/3. And so dividing by 4/3 is the same as multiplying by 3/4. So I've got 3/4 of that term. And then I have to subtract t to the power of, it'll be -1 now, divided by -1 again, and then plus my arbitrary constant c. So we got to tidy this up a little bit for sure. Let's see, 6 over 4 I can reduce to make 3 over 2. So then when I put all that together, I'm going to end up with an answer here that looks like 9 over 2 times the cube root of t to the power of 4, and then subtracting a negative here is going to be plus 1 over t plus my arbitrary constant c. Okay? So a little bit to that one. Let's try the next one. So the first thing I'm going to do with this next one is, so I don't get it too confused, I'm going to change colors again here. So for this next one, the first thing I want to do is represent it again in a nicer form. So let's call this the integral of, so we've got z times z to the power of 1/2. So they're multiplied together. Plus 1 over, so this is z times the cube root of z. So what that is going to be equal to is z times z to the power of 1/3. And we're going to keep all that inside our integral, so the dz has to stick around. And still we can make that nicer if we want to integrate it as a polynomial. We're going to call this the definite integral of z to the power of 3 over 2 when I add those exponents, plus z to the power of, so this 1 over here is also going to be, that's going to be 4/3, so I've got to make it -4/3 to get it out of the denominator. So we've got z with a couple of fractional exponents, dz. Alright, so let's tackle that now. That's going to give us z to the power of 5 over 2, divided by 5 over 2, or multiplied by 2/5. And then I'm going to have plus z to the power of, let's see, negative 1/3 when I increase that by 1, and then divided by 1/3 or multiplied by negative 3. So I've got to put negative 3 out in front here. Should have left myself a little more space. And then we're going to add an arbitrary constant c to that. Okay, so let's tidy that up a bit then. We've got 2 times the square root of z to the power of 5 divided by 5 minus 3 over the cube root of z, and that's going to be plus our arbitrary constant, and then there's your antiderivative. All right, so for this last one looks like it's going to take a little space because there's this exponent here. It means we've got some work to do. So what I'm going to do is I'm going to clear off some space from the previous question. So if you haven't got that, get it down or pause and take it or something. But let's get rid of that a little bit of space so make some room for us here. Make sure we have enough space to do this. All right, so this one looks like it's going to be a little bit to it. Here we go. Alrighty, so for this one, I'm going to first rewrite this as the integral of, that's the ugliest integration sign anyone's ever made, so we're going to have the definite integral of x squared minus 1 squared will be x to the power of 4 minus 2x squared plus 1 divided by x all squared, which is x squared, and then times dx. And so if I divide all 3 terms in the numerator by x squared, I'm going to have the integral of, let's see, x squared minus 2 plus x to the power of minus 2, and then dx. So that's all 3 terms from my numerator divided by x squared. That's what I get. So now if I want to integrate that, or antidifferentiate it, I get x cubed over 3 minus 2x plus x to the power of minus 1 over minus 1 plus our arbitrary constant c, which we can quickly simplify to give us x cubed over 3 minus 2x minus 1 over x plus our arbitrary constant c. So there it is as an antiderivative. Okay, so lots of fun with that stuff. Polynomial-like functions. Now, this is kind of the extent of as far as we can go with finding antiderivatives. We do not differentiate things that we can't make look like polynomials or antidifferentiate them, not in this course. There are lots of ways to do that, of course, but it goes beyond the scope of what we do here. So if it's not something you can make look like a polynomial, it's not something that we antidifferentiate, okay? So let's move along now. Here's your turn question. So similar to the stuff that we were just doing, lots of fun. So if you want to pause and work it out, go for that. And here are the worked out solutions with everything all put together for you. So enjoy those. And then we'll just highlight some of the key things that we saw here. So some of the ideas are, basically it's just a more common way to write an antiderivative is as a definite integral. So just using the dx and the integral sign, and it's the same process as before. So we just update, it says here, our table of antiderivatives to write them in integral notation, all that stuff that we went through. So if you want to take time to look through those, these are not the kind of things I would spend time memorizing, but make sure you understand them because you use them so much you don't really have to commit them to memory. They'll be there anyway. So make sure you understand them. That's the big thing. And these rules are all that's required to integrate any polynomial function or function that can be written in the same form as a polynomial. And we don't integrate anything else, so for this course, you should be safe with just those rules. Okay, so all the best of luck with your studying. If you have any questions, post them on D2L, and I hope that was helpful.